Hello and welcome to our session for physical sciences. My name is Temba Ngube. Today we will take a look into, the series resistors. So we shall be exploring exactly what happens in terms of, the rate of flow of charge, the potential difference across a typical, series circuit. Also, we'll try and explore, a number of skills in as far as measuring is concerned, which is a very, very critical component of, of science. So we'll try to arrive at certain conclusions and also try to discover a lot of exciting facts with regards to the series circuit. But remember, by now we most certainly aware of a number of aspects. We know what potential difference is all about in terms of the amount of work done or the energy transferred per coulomb of charge. We also know something about current. That current has to do with how much charge passes through a point per unit time. And when we talk of a unit time, we're actually talking about a second. Now let's look at the broader overview and try to locate the series resistors in as far as the broader electricity section is concerned. Right. Okay, so without any waste of time, so we're already familiar with potential difference, which is the voltage, which has to do with work done per coulomb of charge, okay? We're also aware that batteries are the source of energy because we've indicated the fact that in as far as the circuit is concerned, we are familiar with the fact that the battery is the primary source of chemical potential energy. And then that energy has to do with the EMF, which is a form of potential difference, which has to do with the maximum amount of energy that can be dissipated by a source for every coulomb of charge, right? So we also familiar with the fact that conductors are actually poor insulators, and insulators are actually poor conductors. So we use different materials to say, okay, charge needs to flow through a material that displays certain physical properties, okay? So, but our focus for today is specifically on circuits. But which aspects of circuits are we looking at today? We're looking at series circuit with respect to resistance, because this is what it's all about. So this is our focus for today. Right. Now, this is the thought that's going to guide our discussion for today. Okay, have you ever thought about what happens to the magnitude of current? Okay, I'll underline that. That's the main idea. So when we talk about magnitude of a quantity, we're actually talking about its size, how much current passes through a point per unit time. Okay, when we have more resistors connected in series. Okay, now the second thought that's also going to guide our discussion has to do with what happens to the terminal potential difference. That's the voltage. Okay, in a series circuit when more than one resistor are connected in series. So the arrangement in terms of connection is going to be the series type of a circuit, right? Okay, now these are the keywords. Now, before we speak to the keywords, there are certain, very important facts about, the definitions that we need to remind ourselves of. The definitions have to do with the terminology, and the terminology is essentially about the language that's going to be used, in our discussion. So if you understand the terminology in the context of electric circuits, even understanding the concepts and even trying to discover some of these facts that we want to bring forward today, I think it becomes very important. But remember, our primary source of definitions is the examination guidelines. Different sources would define the same concept in different ways, but in terms of what is acceptable, it's actually, what we derive from the examination guideline. So it's an all or nothing kind of an arrangement. What do we mean? It's either you know the definition or you do not, right? What are some of the keywords that we're going to use once too often than others today is a resistor, which is actually a device. So a resistor is a device or an electrical component, okay, right? While resistance is a quantity, very important distinction between the two. You need to actually be able to, differentiate. So a resistor offers resistance, okay? So the two cannot be used interchangeably to refer to one and the same thing, okay? Yes, these are two related terms, but a resistor is an instrument or a device that offers resistance, which is the quantity. Now, if we talk about equivalent resistance, sometimes we'll talk about effective resistance in a circuit. Take note of that, okay? sometimes we talk about total resistance in a circuit, okay? Now, we also talk about potential dividers, potential in the sense of voltage, all right? Okay, while we also talk about a series circuit, which has to do with, you know, the amount of charge that passes through a point per unit time, which has to do with the current and how it relates to the potential difference. So these are some of the things that we definitely want to play around and explore and make some of those interesting discoveries, right? Okay, now let's look at resistance as a concept. So resistance, the symbol is capital letter R for now, okay? We're saying resistance is defined as the opposition to the flow of charges, okay? Now, flow of charges is something that we all too familiar with, I think at this point in time. Would say a resistor offers resistance to current. So the flowing charge is actually the current. So the greater the resistance, the greater the extent of, you know, opposition to the flow of current. So the easier the current flows, the lesser the opposition, the lower the resistance. So these are some of the, you know, logical deductions that we obviously need to think about, okay? So that's what, as far as resistance as per the definition in the examination guidelines, right? So different components we're talking about, you know, electrical devices. They provide varying resistance in a circuit. Let's make a practical example. A light bulb is a resistor. In what sense? What do we mean when we say a light bulb is actually a resistor? We are saying that a light bulb as an electrical component, it offers resistance to the flow of charge, or it offers resistance to the current, okay? Now, the major function of the light bulb is to transform electrical energy to light and most probably some heat, okay? But if you compare the amount of energy transferred, you know, from one form to the other by a heating element, let's say, you know, your geyser, it could be your heater at home. These two are both electrical appliances, but at the end of the day, the amount of heat energy transformed from electrical by a heating device is greater. Hence, there is greater resistance for a heating component than a lighting component. So you'd say, okay, what in terms of energy saving and consumption at home, you'd also think about the fact that a light bulb consumes less as compared to a, you know, for example, a kettle. Okay, this is what we mean when we say different components or devices or appliances, they actually offer varying amount of resistance in an electrical circuit. Okay, so an electrical component that has a high magnitude of resistance, that's high resistance, right, will require more energy. Because remember, in a circuit, it's all about the energy transfer or energy transformation. So greater resistance implies more energy conversion, you know, by that particular device. All right, okay? So electrical resistance is measured in ohms. So the ohm, actually, it's actually the SI unit. So we've also looked at R as the symbol, okay? The unit of ohm is omega from the Greek alphabet. So, but remember, ohm is somebody's name. As a result of that, it should always be an uppercase or a capital letter, okay? Now, how do we define an ohm of electrical resistance? It's when you know, an ohm of electrical resistance allows an ampere. An ampere, it's 1 ampere of current, okay, to pass through a conductor when a potential difference of 1 volt is applied across it. So in other words, we are saying 1 omega, which is the 1 ohm, is actually equals to 1 volt per ampere. Okay, if we say per ampere, we are saying there's 1 ampere of current. And when it's 1 ampere of current, what does it mean? It means, you know, a coulomb of charge passes through a point per unit time, right? Okay, now conductors are objects that have low resistance. Now let's look at the physical properties of materials. This is something that we most probably need to remind ourselves as we look into resistance in series. Remember, in terms of physical properties, they are electrical conductors and electrical insulators, which are different from thermal conductors and thermal insulators. In terms of electric current, we talk of electrical conductors and insulators. Now, insulators will be your plastic material, as an example, that does not allow electric charge to pass through them, or current does not pass through them. While electrical conductors, that's your nichrome wire, your copper wire, as you would establish when we use the simulation, we always use the copper wire. Why? Because it's an electrical conductor. So in terms of physical properties, take note of the function of those electrical components in as far as their use in the circuit. Right. And then how do we measure resistance in a simple circuit? We definitely need a cell or a battery, a conductor, a resistor, okay? A resistor can be any device that, it could be a light bulb, okay? It could be even a light bulb, because a light bulb is a resistor. So this is a simple circuit after all, okay? And then we need an ammeter. We know an ammeter is used to measure current passing through a point, the unit time. We also need the switch to complete or break the circuit. We also know that a voltmeter measures potential difference between 2 points in a circuit, right? Now let's look at exactly how one could measure, the resistance of a circuit, which is also an indication of how the flow of charge is affected in a simple circuit. Now let's go to our simulation and actually model that and see what happens, okay? So we've got a simple circuit here with a source or a cell that has got 9 volts EMF, okay? And then the resistance of the resistor there that we have used is actually 10 ohms, okay? The reason why there is a 0 ampere of current in this circuit is because the circuit is broken, okay? How about if we close the switch and complete the circuit, because that's the primary function of the switch. So if we close that, we can see the conventional flow of current which occurs from the positive terminal to the negative terminal. Now, the current reading of 0.9 amperes, what does it tell us? It tells us that there is 0.9 coulombs of charge that pass through any point in this circuit, even through the resistor, for every second. Right. Now we want to establish how our resistance affects the flow of charge, which is the current. Now let's adjust the resistance of this resistor and make it even, let's say double, and see how the rate of flow is affected, which would also be reflected in the current reading. Okay, so if we double that, let's say to 20, right, you can immediately tell that the current is even lesser in magnitude. You can see there is greater opposition to the flow of charge. Even the current reading is almost half of what we had initially when we had a resistance of, okay, if we make it 20, it's actually exactly half the current, which is 0.45 amperes. And what does 0.45 amperes tell us? It tells us that for every second, there is 0.45 coulombs of charge passing through the resistor per second. Right, so that's a simple demonstration of what it means when we talk about the opposition to the flow of electric charge. Right, okay. Now, let's understand now exactly what it means in terms of resistance. A heating appliance or light bulbs, they offer greater resistance than the conducting wire. So the assumption in our simple circuits that we'll set up today is that the conducting wires have got what is called negligible resistance, which implies that we can choose to ignore the resistance of the conducting wires and only focus on the resistance of other components. It could be your light bulb, it could be whatever heating appliance that you connect in your circuit. Okay, so when a component has high resistance, there is more energy transformed when charges move through that particular component. Right, okay. Now, measuring resistance in practice, how do we then measure resistance? We need to ensure that we measure the potential difference in current through that resistor. So if, for argument's sake, we had, if we can quickly go back to that simulation, okay, now we are able to measure the potential difference across the resistor. In this case, there is our potential difference, our potential difference is 9 volts. And then how much current actually passes through that resistor is 0.45. Now, we are able to determine the resistance of this component by using, if we can quickly go back to our our slides, would understand that for us to calculate resistance, we need the magnitude of voltage, which is the potential difference across the resistor, as well as the current passing through it. By so doing, we are able to determine how many ohms of resistance a particular component offers in a circuit. And remember, 1 ohm, right? We're saying 1 ohm, okay, which is the SI unit of, of resistance, is equals to 1 volt per ampere. So this is where it comes from this mathematical equation. Right, so that's as far as determining resistance. So when we come back, we'll try and explore how current varies or potential difference, what happens to potential difference in a series circuit where we have got multiple resistors that are connected in series. Let's take a short break for now.